Alright, so we introduced this one yesterday, but we're actually going to go through it and do the examples for it today, the alternating series. I know we may have wrote a few notes down on it, but I'm going to go back over it briefly, and so you can write down anything you may have missed. If you didn't get a note card, you can get a note card to write down anything you missed. But talking about an alternating series, so we talked about it yesterday. The alternator is what's in front. So it's like the -1 to the n or the -1 to the n plus 1. So they can either look like -1 to the n, like I said, -1 to the n plus 1, or -1 to the n minus 1. Those are some of the alternators you could see within your problems. And we mentioned that this looks like what test? It looks like the nth term test. So we're actually going to be using the nth term test along with this one. So whenever you're doing the nth term test part of it, you ignore alternator for nth term test. When we get to the examples, that'll make a little more sense. Okay, and then the alternating series test, we went through this yesterday, but if your an is greater than 0, the alternating series, right there's your alternator, this needs to be separate from your an. So if you have a function, we're going to see down below, that actually needs pulled out. So you're going to pull your alternator out of those. Okay, so if this one converges, if it converges, the following are true. So this one here, the limit of an equals 0, this really is doing the nth term test. But how does the nth term test work? You just reviewed some of them. Okay, if the limit of an is not equal to 0, what's true? Yeah, if it doesn't equal 0, we know it diverges. If it's equal to 0, it's going to be part of this problem then, okay? And like 99% of the time, if this part is true, then the second part will be true. The an is decreasing or non-increasing sequence. So that is each term that follows the term previous is larger than that term. So about 99% of the time that will happen. You're probably not going to see many scenarios where that does happen. Alright, so note, this does not say if the limit of an is not equal to 0 that the series diverges by the AST. So the AST can only be used to prove convergence. Okay. So if the limit is not equal to 0, what test is that? We just talked about it. Yeah, so if you conclude that it is not equal to 0, it doesn't diverge by AST, it's going to diverge by what? The nth term test. Okay. Alright, so let's go ahead and just look at some examples now. So determine whether the following series converge or diverge. So again, do we see an alternator in this problem? In the first one? Yeah. It's this -1 to the n plus 1. That's our alternator. And when we first check, because we always try the nth term test first, we said to ignore what? So we're actually only looking for this part over here right now. So we're going to take the limit as n approaches infinity of n over 2n minus 1. And if you take the limit of that, you get what? Think of your coefficients. Go ahead. 1/2. Now think about your nth term test, because that's what we were actually doing there. What can we conclude? Think about your nth term test, because that's what we're trying first. You need to look back. Why does it diverge? Yeah, it's not equal to 0, so it diverges by nth term test. So we're done. We don't even have to go on to the alternating series test because we concluded by the nth term test that it diverged. So that problem's done. All right, we'll go on to the next one. Do we see an alternator in this one?
Yes.
Yeah. It's that negative 1 to the n. So this is all going to stay separated here as we do the nth term test. So limit n goes to infinity, n over ln of 2n and this limit's actually going to go to what? Which one is growing faster? The top's growing faster, so it's eventually going to get to what? Infinity. Very good. So now what can we conclude about this one? Yeah, we just learned the alternating series test, but we haven't even had to use it yet. So it also diverges by nth term. Nth term test. All right, so let's go on to the third one. Do we see an alternator?
Yes, since the cosine happens to be.
Okay, do we blatantly see one out there, like one of these ones up above? No. So at first thought, you might think, well, this doesn't alternate. But what were you going to say there? Or what?
Cosine alternates between positive and negative.
Yeah, as you plug in values for n, it's going to keep alternating back and forth between what two values? What two values will cosine alternate back and forth between? Yeah, it's going to alternate back and forth between -1 and +1. So we're actually going to take the limit of this. It's going to alternate back and forth between positive and -1. So if we know the top is going to be somewhere between -1 and +1, and we're taking the limit as n goes to infinity, what would the limit of that be? 0. The bottom's going to keep getting bigger. Yeah, exactly. So that was the nth term test. I mean, that's what we were trying to do, is the nth term test. Did that help us, according to the nth term test? No, because if it's not equal to 0, it diverges, but it is equal to 0, so by the nth term test, we know nothing. But what do we know by the alternating series test? Yeah, so it converges by the alternating series test.
We can't figure out what it converges to.
No.
Can you explain the second thing, not the up top, that second thing, the
Here?
whole, yeah.
So basically what they're saying is this is going to keep going back and forth. So if you look up here, we have, technically there's a plus here, so plus, minus, alternating back and forth. But what they're saying is it's going to be decreasing. So as you go on with your values, each value has to be getting smaller or non-increasing, so it has to be at least staying the same. So we can't go from like 1/2 to a value that's bigger of 1 here. It has to keep getting smaller or at least stay the same. Because if it's getting bigger, you start adding stuff to it. Okay? And if you start adding things together, you're not going to converge, but you would diverge. Does that help you a little bit?
Yeah.
Okay. Let's go to letter D. All right, so do we see an alternator in this one? Yeah, we do. So we want to separate that out, but what's left on the top? Yeah, if we get rid of that alternator, we're left with a 1 on the top. And the limit? So what is our conclusion?
Converges.
By what?
AST.
Yes. So once you really have an idea of what these tests are and kind of at least the gist of them memorized, I think the hardest part will be picking out which test it is. Then once you have a test, you have a direction to go in. All right, are we good for the next one? So once again, we have that alternator on top. So we're separating it out. Well, we would just have a 1 left on top. Limit. Is the bottom getting bigger? Or keep getting bigger? If it does, what are we approaching then? Yep. So like before, converges by what?
AST.
Yep, alternating series test. And lastly, I think you can do the last one on your own. If you take the limit, you get what?
0.
0. So once again, converges by AST. Not too bad. Are we okay to move on then? All right, so if you flip over, what we're going to talk about now is absolute versus conditional convergence. And we have a little bit of space at the top, so we're actually going to write a few things at the top here. So we're going to consider the sum from 1 to infinity of an. Okay? We're going to say two different things about it. So consider the sum from 1 to infinity of an. Alright, so all terms are positive anyway. So the absolute value does nothing. So what we're writing is going to refer to the theorem below. So all terms are positive anyway, so the absolute value does nothing. The second thing, some terms negative, which makes an less than the absolute value of an. and by the direct comparison test, DCT. If the absolute value of AN converges, so will AN. So basically what the second one is saying here, if you have some series and you're adding your terms up, and maybe it's like the alternating series, you have some terms that are being subtracted away. If you take the absolute value of that, that's going to make all your terms positive now. So instead of alternating, all your terms are going to be added up. So, like the direct comparison test, we have two things now we can compare. If AN would converge, it's bigger now because we added all the terms instead of subtracting some of those terms away. If the absolute value one converged, then you know AN will also converge because it's smaller. Okay. The top one, if it's already all positive, the absolute value is not going to do anything to it because your terms are already positive. So you're just adding the terms. Take the absolute value, you're still adding the same terms. So that's what those 2 points mean. So let's actually talk about the theorem then. So basically what we said above, but if the series from 1 to infinity of the absolute value converges, then the sum of just AN will also converge. Like I said, the absolute value will be larger than AN, or it will be the same. If the terms were already positive, you take the absolute value, it's going to give you the same thing. Alright, so such a series is called absolutely convergent. Notice that if it converges on its own, the alternator only allows it to converge more rapidly. Does that sentence make sense to you? Read that again on your own, maybe. Are we all okay with what that's saying? Okay. So it's converging on its own allows it to converge more rapidly. That's because we have those terms that are subtracting in there. So if you're subtracting terms off of something that already converges, well, obviously it's going to converge faster. Okay. So with this one, this diverges when you take away the alternator. So taking the absolute value of that, that's making everything positive. You're taking away that alternator. But with this one right here, this is saying that this one is converging with the alternator. Okay, so it's conditionally convergent. If AN converges, so with the alternator, you have your pluses and minuses, it converges. You're subtracting things away. But if you take the absolute value and you get rid of the alternator and it diverges, then it's known as conditionally convergent because it will only converge if you have those terms subtracted away. So we have these two that we talked about, absolutely convergent and conditionally convergent. The absolute is if you take the absolute value and they both converge. But if you take the absolute value and then it diverges, your series is only conditionally convergent then. So you have two possibilities here. Alright, I think it's more easily seen with an example. So determine whether the given alternating series converges or diverges. If it converges, determine whether it is absolutely convergent or conditionally convergent. So on the first one, what would be the first step in checking this? We need to do what? What does it look like? What test that we've done does it seem similar to? Hint, we may have done it today. Alternating series. So we separate that alternator away. So we take the limit And that limit is what? 0. Okay. So far, it's equal to 0, so we know what. Our conclusion is what on this part? Converges by AST. So we know with the alternator it is converging. We want to know if it is absolutely convergent though. So if we take the absolute value and it converges, then we know it's absolute convergence. So we're going to take the absolute value, -1 to the n over square root of n. Well, the absolute value gets rid of that alternator, so you're left with 1 over square root of n. Now, we can't do the alternating series test now because we don't have an alternator. All we're left with is 1 over square root of n. So now, what test does this seem similar to? We no longer have the alternator, so we have to use a different test for this. Do you have to look back through your note cards? P-series, yeah. So if we use the P-series, our exponent on the n is what? Okay, so we know our P is 1/2. Does that tell us diverge or converge? Yes. Diverge by P-series with P equal to 1/2. So is it conditionally convergent or absolutely convergent? Yes, conditionally. Very good. So after seeing that example, does that make a little more sense on what we're talking about there with the absolute versus conditionally? All right, let's try the other one. So on the second one, we recognize the original problem as what? What's present that makes the beginning of this easy? Yeah, it's an alternating series. So take the limit. Limit goes to 0. So it converges by what? Okay, by the alternating series test. Yes, that's what we used. So we know that this converges, but we want to test whether it's absolutely convergent, so we have to take the absolute value. So if you take the absolute value of that above, you're actually trying to find 1 over 3 to the n. So what test does that look like? See if you can recognize the test without looking. It is a geometric series. Geometric series is, or how can you recognize a geometric series?
As the
Ratio to a power. So what would be our ratio here? Like, I don't actually see a ratio to a power. I see a denominator to a power. Can,
Put all of 1/3 to one.
yeah, since it's just the 1 on top, you can raise the whole 1/3 to the nth. Now we have a ratio to a power. So now we can use our geometric series test. Well, how do we actually use that test now? It's been a while. That was the first one. If you have to look back, you can. Caitlin?
The absolute value of R is less than 1, so it's convert.
Yeah, you look at the absolute value, and the absolute value, let me go back here. If the absolute value is less than 1, it converges. Okay, so we say it converges. Converges by, and we used a geometric series test. Now, it didn't ask us what it converged to. Could we find it, though? Yeah, we could. It would be the first term over 1 minus r. Okay, but all they're asking for is conditionally convergent or absolutely convergent, so the answer is what?
Absolutely.
Yes. Exactly. Do we have any questions about any of those? All right, so we're finished a little earlier than I expected. That's where I want to stop for today. Tomorrow we'll move on to the alternate series remainder. So we'll finish the notes up on that tomorrow, and then we'll probably move on to the ratio and root tests. Okay, so we're getting close to the end here.